We're going to try number 63 next. So an antifreeze and coolant widely used in automobile engines is 38.7% carbon. So automatically we assume 100 gram sample. So I just convert that into grams. 38.7 grams of carbon. And the 9.7% hydrogen changes to 9.7 grams of hydrogen. And then 51.6% oxygen goes to 51.6 grams of oxygen. Now, I don't use H2 and O2 here. Do you know why? Yeah, we're not using like hydrogen gas and oxygen gas. Like when you buy antifreeze or coolant at the auto shop, it doesn't contain any hydrogen and oxygen gas. It contains hydrogen and oxygen atoms, like water does, but water doesn't consist of the gases, the elements themselves. And so this is it. So I can get a mass ratio here. The mass ratio would be about 40 to 10 to about 52. That would be the mass ratio. But are formulas mass ratios or mole ratios? Formulas are mole ratios. So the first step we have to do is convert it from grams to moles. And so for carbon, 1 mole of carbon weighs 12.01 grams. This is from the periodic table. So grams of carbon cancel, and that gives me moles of carbon there. So that would be 38.7 divided by 12.01. That gives me 3.222 moles of carbon. I have more C3s than allowed. And then here I have 1 mole of hydrogen, H, weighs 1.008 grams. This will give me 4 C3s here. So probably I'm okay with 3. So it's going to be 9.7 divided by 1.008. Which gives us 9.623 moles of hydrogen. And then oxygen, 1 mole of oxygen weighs 16.00 grams. So this is going to be 51.6 divided by 16, 3.225. And so what should I call it? Does it look like C3H10CO3? What do you think? Should I round that? So this is going to be C3.222, H9.623, O3.225. So should I just go ahead and round this to C3H10O3? No, I think that would be too much rounding. No. And so rather than rounding it now, what should I do? Divide by the smallest. So this is going to be 3.222, which is the smallest. So 3.222 divided by 3.222 is going to give me 1.000. H, 9.623. 9.623 divided by the smallest, which would be 3.222, comes out to 2.986. So I'll have 3.225 divided by 3.222. This is going to come out to 1.0009. So here I feel more comfortable. We can round this to 1. Hydrogen, I can round that to 3. And then oxygen, I can round to 1. And so I get CH3O versus C3H10O3. You see, it's a 1 to 3 to 1 ratio, which this is just slightly more for the hydrogen. And so this one looks good. This is called the empirical formula, which would be the simplest mole ratio. Empirical formula is the simplest whole number mole ratio. Simplest whole number mole ratio. And so 1 carbon, 3 hydrogens, 1 oxygen, either moles or single atoms. Now, when I have a compound that's made up of all nonmetals, that's typically a molecular compound. Molecular compounds are made up of all nonmetals. Ionic compounds are made up of metals and nonmetals. When we have a molecular compound, that usually occurs in discrete molecules. And so here it says a mole of these molecules weighs 62.0 grams per mole. And so we can take this one step farther. And so what we're going to get is something called the empirical mass or the empirical formula mass. And so empirical formula mass is this. We have 1 carbon that weighs 1201, 3 hydrogen that's going to weigh 303, and 1 oxygen, which is going to weigh 1600. And so if I look at the empirical unit there, that's going to weigh 4, 0, 5, and 6 is 11, 30, 3104. And so the empirical formula mass is 31, let's say. But if you weigh a molecule, it weighs 62. And so the molecular formula mass is twice as heavy. Is 62.0 grams per mole. So it's twice as heavy as the empirical unit, and therefore the molecular formula must be twice as big. So it's going to be C2H6O2. If I weigh this, this should weigh 62. So 2 times 12 is 24, plus 6 is 30, plus 16 is going to be 62. 30 plus 32, and 16 times 2. And so this unit weighs 62, which matches. So this would be the molecular formula. Some people will do the ratio. Sometimes it's not so clear. So if we take the molecular mass and divide it by the empirical mass, then we get a multiplication factor. In this case, the molecular mass is 62, and the imperial mass is 31. And so we get a factor of 2. Factor of 2 means the molecular formula is double that of the empirical formula. This would be half the molecule. And so hydrogen peroxide is H2O2. And so a molecule of this looks something like this. But if we cut this in half, we'll form the empirical formula. The empirical formula is the hydrogen peroxide that's been broken in half. It's no longer hydrogen peroxide. And so the empirical formula is this. The empirical mass would be 16 plus 1 is 17. Hydrogen peroxide, the molecular formula is this. And the molecular formula mass would be 16 times 2 is 32 plus 2 is 34. So there's going to be a difference in masses. So the molecule weighs twice as much as the empirical unit. And so I'm not going to have a half a molecule of hydrogen peroxide. It doesn't exist. So this is the correct formula for hydrogen peroxide. This is not. This would be the correct formula for this antifreeze. This is no. But when we do the math, we get the empirical formula. In order to get the molecular formula, we need to know how much it weighs. How much it weighs, we have to be given that, or we have to determine it some other way. Okay, any questions on this? All right. Why don't you try number 66? Here. You can do this on this card. A compound is found to contain 25.24% sulfur and 74.76% fluorine by mass. What is the empirical formula for the compound? Okay, but they give you some additional data. The molar mass for this compound is 254.1 grams per mole. What is the molecular formula for this compound? So we want to figure out the empirical formula first and then the molecular formula. For example, the stoichiometry math shows this. In this chapter, we're doing mass of A. So we have, let's say, grams of A, like grams of sulfur. In order to go from grams of A to moles of A, we need the molar mass. And so the molar mass will take us there. We can go either way. We can go forward or backwards. So we'll flip over the molar mass if we want to go from moles to grams or grams to moles. And then we often go, in this particular chapter, we go one more step, and that is to the number of A particles. So number of particles of A. If A is a molecule, then the number of molecules of A. And in order to do that, we need another conversion factor. The other conversion factor here is going to be Avogadro's number. You know, Avogadro's number is abbreviated N sub A. But are we doing that in this particular problem? In this particular problem, we're just going from grams of A to moles of A. And so we end up with moles of sulfur. Here, how many sig figs are we going to get in moles of sulfur? 4. And so you can write those out. And then we do the same thing here, 74.76 grams of fluorine. 1 mole of fluorine weighs, to 4 sig figs, it's 19.00 grams. And that gives us the mole of chlorine. And then we get the simplest. There are some tricks to getting the simplest whole number ratio. The easiest trick is to divide by the smallest. We divide by the smallest. And so we might end up with something like this. SF 4.99. If we ended up with something like that, what should I do? Should I go ahead and round that to SF5 or should I leave it? I'm going to round it. I'm going to call this SF5, right? But what if this were not 4.99? What if this came out to SF 4.5? Would you round this to 5? No, I probably wouldn't round this. You know what I'd do? I wouldn't divide it again because, you know, the smallest is 1 now. And if the smallest is 1, then it's not going to make much of any difference here. So I wouldn't divide it by 1. Instead, I multiply it by 2. Yeah. If I multiply by 2, I'm going to get S2F9. You know, and that works out to simple whole numbers. What if it came out to SF1.33? You know what I do? Should I round that to SF1? No. Multiply by 3. I'd multiply this by 3. So this one I'd multiply by 2. This one I'd multiply by 3. And then I get S3 F7. Or no, not 7. 4, F4. You see that? Mm-hmm. What if it came out to SF 1.67? Should I round that to 2? No, I'm not going to round that. You know what I'm going to do? Yeah, I'm going to triple it. That'll get rid of that. And that'll bring it close to whole number. Yours came out, some of yours, depending on how your calculation went, it was right on, 5. So we don't have to worry about it, or close, 4.99. So if we have SF5, this unit, how much does this unit weigh? It weighs 127. But the actual molecule weighs 254, so it's got to be twice as heavy. So this is why it's doubled. And so if this is 127, S2F10 is 254, so that matches. We want both answers. We want the empirical formula and the molecular formula. Obviously, the molecular formula is the best because it's the most informative if it's a molecule. So, for example, hydrogen peroxide. Do you know what the empirical formula for hydrogen peroxide is? The empirical formula is HO.
Oh, yeah. But
there's no molecule HO. Hydrogen peroxide is actually H2O2. We can tell when we weigh an H2O2, when we weigh hydrogen peroxide, it weighs 2 times 16 is 32, 34. This weighs 34. So we weigh this molecule in mass spectrometer, it comes out to 34. However, if we weighed this unit, how much would it weigh? This is 16 plus 1. This is only 17. And so if we know hydrogen peroxide weighs 34 and we get this as the formula, could this be hydrogen peroxide? No, this is not. This can't be hydrogen peroxide because it doesn't weigh enough. The actual hydrogen peroxide is twice as heavy, and therefore we'd have to double it. And so this is hydrogen peroxide here. Does that make sense? Okay. So we do the same thing over there. So we can try to finish that. Okay, so in this chapter, this is, there are a lot of problems. Gram to mole conversion and mole to gram conversion. So it's just a single step dimensional analysis. The conversion factor is the molar mass. Or mole to number or number to mole conversion. That's also a one-step conversion. Since we have these one-step conversions, let's try to do something a little bit more difficult. A little bit more challenging. And a little bit more challenging, maybe a two-step, rather than just doing one of these steps. Let's try to do 2 steps. So we'll go from grams to moles to number, or number to moles to grams. We'll try that. And so the more challenging problem, we'll have 2 steps. The quantitative significance of taking a deep breath varies, of course, with the individual. When one person did so, he found that he inhaled 2.95 times 10 to the 22nd molecules. How the heck do you get that? If you take a deep breath, can you count how many molecules you just inhaled? No. So this is not a realistic problem. This is some kind of hypothetical thing. Okay, 2.95 times 10 to the 22nd. There are 2 things that make this challenging. One, there's 2 steps. And 2, this is 2.95 times 10 to the 22nd molecules of air. Is air pure? No. Air is not pure. Air is a mixture of what?
Nitrogen and oxygen.
Yeah, and is that ratio, is the percent nitrogen and the percent oxygen fixed? That is, it's always the same? Exactly the same? So air here in LA is exactly the same as air in Tibet, or air on Everest, or air in Detroit, Michigan? No, it varies a little bit. And so, but anyway, we can have this many molecules of air, and it's going to consist of nitrogen molecules and oxygen molecules mainly. Assuming the mixture has an average molar mass of 29 grams per mole. So if we took a mole of these molecules, it would weigh on average 29 grams. A mole of molecules is like 6.022 times 10 to the 23rd. So we have 29 grams of air. This is an average per mole of air. Now it depends, there are other components in the air, and there could be pollutants in air too. So this is only get to 2 sig figs. It's a mixture. And mixture compositions aren't fixed. Mixture composition varies. And so the conversion here is we're going to go from molecules of air to moles of air to grams of air. So, assuming this mixture has an average molar mass of 29 grams per mole, what is its apparent loading capacity in grams of air? Okay, so we're going to go from molecules to moles. And we'll use Avogadro's number for this. 1 mole of air molecules is 6.022 times 10 to the 23rd molecules of air total. So molecules of air cancel out, and that leaves us with moles of air. And then we're going to use the molar mass. There's, on average, 29 grams of air per 6.022 times 10 to the 23rd molecules, which is a mole of air. And so moles of air cancel, and that leaves us with grams of air. So this is a 2-step conversion, which is common in this. This is stoichiometry. Stoichiometry is quantity relationships, and it's just dimensional analysis. So let's go ahead and calculate how many grams of air was inhaled. It would be 2.95 times 10 to the 22nd divided by 6.022 times 10 to the 23rd times 29. 1.42. How many sig figs? I'm allowed 2 sig figs, so I'll just carry 1 extra. 1.42 grams of air, or 1.4 grams of air, since the molar masses only get to 2 sig figs. Since it's a mixture, it's not pure. So 1.4 grams of air. Let's take a look at the next one. Assuming gasoline to be pure octane. Is gasoline pure octane, or is it a mixture? It's a mixture. The gasoline's going to contain a whole bunch of different things. But what they're asking us to do here is we're going to assume that the gasoline's pure octane. Octane is C8H18. Now, this is what we call a binary molecular compound. It's a binary. Binary means 2 elements. It's molecular because compounds of nonmetals, carbon's a nonmetal, hydrogen's a nonmetal. Compounds of nonmetals are molecular compounds. That's a rule. That's not a law. So there are some exceptions. And so we should name this according to the rules of binary nomenclature, binary molecular compound nomenclature. How would you name this? We'd call this octacarbon. And what would 18 be? $18 would be, I used to know. I used to know through the teens and the 20s, but I forgot. I forgot because we don't name it that way. This is called, organic has their own way of naming things. This is called octane. Octadeca? All right, thank you. So this would be octacarbon, octadecahydride. Is that right? Okay. An automobile getting 25 miles per gallon. 25.0 miles per gallon of octane. would consume 5.62 times 10 to the 23rd molecules per mile. Consumes 5.62 times 10 to the 23rd molecules per mile. How did they measure that? No idea. When you're driving down the road, are you counting how many molecules are combusting?
You really shouldn't. That's very distracting.
I mean, and not only that, can you count that fast? No. Okay, calculate the mass of this amount of fuel. So we want the mass of which amount of fuel? 25 miles per gallon, so a gallon of fuel? Or do we want the mass of 5.62 times 10 to the 23rd molecules worth of fuel? Yeah. In this case, are we even going to use this? We're not even going to use this. Why did they give this to us? The reason they gave us this number is because this is the mileage you get, at this 25 miles per gallon. Yeah. Well, anyway, this is the mileage we get in terms of molecules. But molecules is so weird that they're going to use this anyway. So this is molecules of octane, C8H18 per mile. And so we aren't really going to use this here. And so here we're going to go from number of molecules to moles using Avogadro's number. And so 1 mole of octane, C8H18, contains how many molecules? Well, it contains 6.022 times 10 to the 23rd C8H18 molecules. So we have moles of molecules per mile. And then from moles, we'll just go to mass. So we'll need the molar mass of octane. The molar mass of octane, we have 8 carbons, and then carbon weighs about 1201. So this is going to give us 9608 grams per mole. And then we have 18 hydrogens. So it's going to be 18. In this case, I'm going to use 1.008 for that. And this is going to give me 18.144. And so add these two up, I'm going to get 12, 22, 14, 114.22 grams per mole, or U per molecule. And so 114.22 grams of octane per mole of octane. And so moles cancel, and that leaves us with grams, and that's what we want. So 5.62 times 10 to the 23rd divided by 6.022 times 10 to the 23rd times 114.22. So I calculate 106.59 grams per mile. So how many sig figs are we allowed? 3. So I calculate 107 grams per mile. It consumes 107 grams per mile. Usually you don't buy gasoline by the gram, do you? No, we buy it by the gallon. And that's going to be the next level. The next level would be to figure out the volume. We'd need to know the what? In order to go from grams to milliliters, we would need to know the density. So if we had the density, then we could calculate how many milliliters, and then milliliters to liters, and the liters to gallons. We could figure out how many gallons that is per mile. It's a simpler way of doing that, but it's not. You know, so speaking of fuel economy, I was looking at, Tesla. When you have a Tesla, they give you like the projected savings. It's one of their marketing type deals. Projected savings, how much you save by driving a Tesla in dollars. But then I looked at their calculation, and they're like, for example, you plug it in at your home, and then it'll tell you how many dollars it costs you to charge at home, which is cheaper than supercharging stations. Supercharging is like a lot more expensive. And so I charged it, and it was only like $3. $3, that's pretty good. It was from 36% to 80% charge. $3 is pretty cheap, because that can take you, at least over 100 miles probably. But then I looked at the what they're using for the electricity rate. They were using 13 cents per kilowatt hour for their calculation. 13 cents per kilowatt hour. And then I looked at my electricity bill. My electricity bill is over 40 cents per kilowatt hour. And so it wasn't like $3. No, it's much more than $3. It was like 4 times more than $3. It was like $12. And then when you put it in that context, maybe, it's hard to say, as far as saving money. I'm not sure, because maybe a hybrid could give you the same kind of cost per mile. Hybrids are getting 50 miles to the gallon now. Yeah. And so it's a hard call. Is it cheaper?
You can write a script.
Hmm?
You can write a script. Tell you.
Yeah, that's true. You can do that.
I would probably think it's cheaper because it goes around $13 for 100 miles, and it's $14 for me to put 2 gallons in the tank.
Okay. 14.
It was 14 like 2 days ago for me at least at my gas station.
You also have to factor in Teslas are like really expensive.
Yeah, Teslas are really expensive, and then
You have to factor in that extra $20,000 you're going to spend on it. How long is that going to take you to make that back off of electricity?
yeah, but then other people will argue that it's carbon. You're producing less CO2, which may or may not be true, because it depends if the electricity is generated from combusting coal generates CO2s, and then converting that heat into electricity is not 100% efficient. You lose some energy there, and you end up making more. Whereas now combustion engines, like and hybrids, they're very efficient.
These solar panels on your house.
Yeah, solar panels. So that's why nuclear seems like good option. Nuclear fusion. They're talking about the fusion reactors. In fact, I watched this little thing about one of these fusion reactors. But this environmental impacts on everything. One of the fusion reactors is using this. What's this one?
Hydrogen.
Deuterium.
Deuterium.
They're using helium-3. And so you have to source the helium-3. Apparently they're saying helium-3 is fairly abundant. There's been up and down shortages of helium. You used to go to Party City and be able to buy a tank of helium, but then all of a sudden there were no tanks. Do you remember that? It's because of the helium shortage. There's a helium shortage. There's a fixed amount of helium or limited amount of helium, unless they start making more. But it's made from nuclear processes. But this was pretty promising, because this was a new fusion reactor. I'll bring in the article. I saw the article, and so it looked pretty good. And this makes helium-4, which is very stable, and a neutron. And so one of the big benefits of fusion, like fusion from the sun, is it makes helium. Helium, is it very reactive?
No.
No. I mean, is it poisonous? No. Is it a pollutant? No, not really. No. So it's good. Except for this isn't so good. Neutrons. Neutrons aren't that great. If it produces neutrons. Have you ever heard of the neutron bomb?
Yeah.
The neutron bomb is an idea that what you do is you drop something that produces lots of neutrons, and the neutrons kill all the living things, but leaves all the buildings standing. It doesn't destroy the buildings, and so all the infrastructure is still there. But the problem is this. Why are neutrons so damaging? Well, it's because, do you remember the gold experiment? Who was that did the gold foil experiment? Remember who did the gold foil experiment? Rutherford. And what did Rutherford do? Yeah. And so the alpha particles, do you know the alpha particles, are they neutral or do they have charge? They have charge. In fact, alpha particles are the nucleus of the helium atom. And so it's a helium minus the 2 electrons, which means it's He2 plus. And what they did was they went close to the gold nuclei. When they got close to the gold nuclei, they were deflected, right? Highly deflected. Or if they went straight in. If they went in straight in, couldn't this, alpha particles are nucleus. So if you have an alpha particle and a gold nucleus, can't they fuse together to make a bigger nucleus? And so you're shooting a tiny nucleus at a bigger nucleus. Can't that tiny nucleus fuse with the bigger nucleus? Yeah, it could if it were moving fast enough, but it's not moving fast enough because what happens is they get deflected. Why do they get deflected? Like charges, right? Like charges repel. And so in order to get those two nuclei to fuse together, you need high energy. And Rutherford wasn't accelerating. If Rutherford had a linear accelerator, which will take that alpha particle and make it faster and faster and faster by using electric fields, to accelerate it, and then you could have a high speed collision. If you have a high enough speed collision, then you can fuse the two nuclei together. But it wasn't fast enough. Or if you have a cyclotron, which does the same thing, you can fuse them together. And so the two nuclei will never react. And so we don't get any nuclear reaction, we just get deflection. That deflection is due to the charges. But you could take a slow neutron. If you take a slow neutron, is a slow neutron going to get deflected? No, a neutron does not get deflected. If a neutron goes straight at the nucleus, do you know what's going to happen? It's going to go straight in and react and fuse. If you fuse too many neutrons into an atom, you upset the neutron to proton balance. When you upset the neutron to proton balance, do you know what happens? It becomes radioactive. And so the problem, the situation with the neutron bomb is this. Even though you're going to kill all living things, because the same thing, the neutrons are going to go into the nuclei of your body and make the nuclei unstable and radioactive, it does it to the buildings and whatever else. And so the neutron is going to make everything radioactive. So when I was listening to this talk, they were saying, well, we're going to make helium, which is great, and then it's going to cause a little radioactivity. And so I was thinking, a little radioactivity, okay, what does that mean, a little radioactivity? Well, a little radioactivity means that the neutrons are going to make whatever structure they're using radioactive. There are ways you can capture neutrons, though. There are neutron absorbers, like boron, other things that love neutrons. So you can capture a lot of neutrons. I'm sure they're working on making it safe. But this is pretty promising because they were talking about the dollar per kilowatt hour. Because $1 per kilowatt hour of nuclear power is pretty cheap, actually. Well, it's pretty cheap if you don't factor in, disasters. Then it's cheap, but. But anyway, so that's something that's not really. but it's getting closer. You know, the reason I caught my attention is they're saying what they're gonna do is they're not gonna have these big fusion reactors. They're gonna have a lot of little fusion reactors. And then they're saying that they're gonna get these fusion reactors online, you know, mass producing them, producing electricity by 2024, I think, or 2023. Can't remember, but I mean, they're thinking they're that far ahead.
What about the Tesla? The magnetic strength of the coils wasn't high enough because the materials didn't have the right superconductive materials to get the Tesla high enough.
The Tesla,
The Tesla is what magnetism is rated at. The magnetic strength of the coils that.
is that for the giga?
I think it was accelerator.
The Tesla, the linear, is Tesla actually working on an accelerator?
No, the Tesla is a unit of measurement.
Oh, you're talking about the magnetic field strength.
Yeah.
Okay, yeah. For this,
I'm not sure if it was fusion or fission. I don't remember.
yeah,
I think it was fusion, but the stellarator fusion coils wasn't strong enough.
to contain the plasma. No, they had a really interesting way that they were igniting the fusion. I'll have to bring the article. I'll show it to you next time, I think. But what is it? I forgot what they called this one. Yeah, this is mining the moon. They're going to get the helium-3 off the moon, I think. But they did something about the fusion. They did something about this. In fact, they had a setup with the confinement of the plasma. But I have to take a look. I didn't see that many details of that. One thing they didn't need is, I guess they didn't need as high, densities to make this operate. But I just saw their marketing video, so I'll show you that. Once I remember the name of the company. Oh, I know what it is. This one doesn't need nearly as much activation energy to ignite, so you don't need as many. So you don't need as powerful of a field to do that. With 1840 versus the traditional deuterium plus deuterium or deuterium plus tritium. Something like that. Okay. Well, anyway, this is pretty much chapter 7 here. So you can take a look at some of the other problems that we'll see in chapter 7. This is something else I saw. This is company C0. Have you ever heard of that? C0. Then I was looking at the news and I saw this C0, and then I looked at who founded the company. And I took a class from this guy at UCSB. This guy was a chemical engineer, so I was taking an engineering class there. And he has an interesting background. This guy is Eric McFarland. And I saw Eric McFarland in C0, so then I thought, oh, Eric McFarland, I remember that class. Because in that class, he took yeast. Well, this was his research when I was taking the class. He'd take yeast cells and then hit them with gamma radiation and then monitored the metabolism of phosphates in there. And I thought, wow, that's pretty interesting because he was looking at radiation damage to organisms. And since I was working with X-rays at the time, so it fortunately wasn't as bad as gamma rays. But still the same kind of thing, ionizing radiation. But he has an interesting, resume or CV, as they call it. He got his PhD in chemical engineering from MIT, and kind of at the same time, he got his MD in medicine from Harvard. So I think he was attending both because he got his PhD and his MD within 1 year, which is just seemed like not feasible, but it was true. I couldn't believe it. Well, anyway, the normal way that hydrogen's produced is this. They take methane and they do this. This is the classic way hydrogen's produced. It's called the water-gas shift reaction. And in the water-gas shift, you take methane and you react it with steam. And so there are going to be some violent collisions there, because this is a very high temperature. And so in this, it reacts to form hydrogen gas. And what? What else do you think forms carbon? Carbon dioxide, exactly. So that's good, you figured it out. This is one of the more efficient ways, of producing it from natural gas. So you could use natural gas to make hydrogen. It's still expensive because you need a lot of energy to do this. But the problem is this, the CO2. So this Eric McFarland's thinking, how can you make hydrogen without making the CO2? Because there's going to be a carbon tax. And so that's going to increase the cost of making hydrogen if you have to pay the carbon tax in addition. Carbon tax is for emitting CO2. And so he says for this, I think you're making a lot of CO2 in the process. Natural gas is cheap and abundant, but today utilizing it for energy generates carbon dioxide. So they have the solution. They're using natural gas here in the proprietary method. The proprietary method is they don't use steam here. They use a hot liquid. And the hot liquid, they don't say what the hot liquid is. It's just they put the methane through a hot liquid. When they put the methane through the hot liquid, they generate hydrogen gas. Okay, the hot liquid is a catalyst. The catalyst just kind of speeds up the reaction. But instead of generating CO2, do you know what they generate? They generate soot or carbon. And so here, with their proprietary method, they're getting rid of the water. And they're just using CH4 and this hot liquid to generate H2 and carbon. The carbon is like soot. And what he proposes to do with the soot is to bury it in the ground. So he wants to bury it in the coal mines, let's say in the coal mines of Utah, Wyoming, Pennsylvania, etc. And so that means there's going to be zero carbon footprint because, they already removed the carbon out of there. He's just going to put the carbon back in the ground. Although you don't have to put the carbon back in the ground. You can just burn this as fuel, like charcoal. But
then that causes
CO2, which means you have to pay tax on that. So his proposal is to put it back in the ground, and when he puts it back in the ground, then it comes out to carbon zero. And so that's the name of the company, Carbon Zero. So I thought that was pretty interesting. Hydrogen's another fuel, for the future economy.
What can you postulate the hot liquid to be?
Some kind of salt. And this salt, you have ions in the salt. And when you have ions, some of the ions pull electrons off. What we want to do is we want to pull electrons. How many electrons do we want to pull off carbon? 4. The carbon here is what's the oxidation state of carbon here? Not +4, -4. So if we can go from -4 to 0, then we just pull off 4. And so what I think the proprietary hot liquid is, it's going to be a molten salt, like maybe molten iron. Let's see what else. We don't want chlorine. We probably want something with iron 3 plus in there, or something like that. Or it depends on, it's got to be iron 3 plus. Usually these salts have very high melting points. And so it might not be iron 3 plus. It might be something lower, But if we have a molten salt, then this ion can attack that carbon and take the electrons in the process, something like that. But if he does that, then that's what we call a chemical reaction, and then we're going to get molten iron. Well, we got molten iron, then we have to deal with molten iron too. So it's got to be something that regenerates. So it might take the electrons and then regenerate it some other reaction. So what's best is a catalyst. A catalyst, what it does is it reacts and then regenerates. So we don't get these other byproducts. And so he's saying this is pretty clean. And so that's pretty interesting. It would be a pretty challenging synthesis problem. So he's saying the only thing that sloughs off is carbon. And so they just take the carbon off, the carbon floats to the surface of the molten liquid, and they just slough it off and then just collect it as waste. And then they can bury it. And so, hot liquid, something that can take electrons. Yeah. In the heat, there's going to be a lot of collisions and other stuff. So there was another thing here. Where I read this was here. I read this in CND News. And we had a story in CND News for this. Well, the Nobel Prize Physiology and Medicine came out. They're predicting who's going to win the Nobel Prize for this. Well, this is the company here, C0. It's in San Jose. C0 raises 11.5 million. This is called turquoise hydrogen. I think the normal way is called brown hydrogen. Oh, here it is. This is really small. Turquoise hydrogen makes carbon rather than CO2. I don't know why they can have all these green hydrogen, turquoise hydrogen, blue hydrogen, and all these hydrogens. I was thinking about getting one of these cars, the Toyota Mirai. Have you heard that? When these first came out, they said they're going to supply the fuel for free. So all the hydrogen is going to be free. I thought, wow, that's a good deal. You can only lease these. You can't buy these. So this is a fuel cell vehicle. It's one of those. That's pretty interesting.
Why do you do electrolysis and make more hydrogen?
You could do electrolysis, but it's very expensive. Like the 9-volt battery, you're spending more money to generate the hydrogen than what you get in fuel. So it costs you more. It's not break even. So that's why they don't do it. You could do if you use like electricity to do it, like off the grid electricity. If you use electrolysis using photovoltaics, then it would be worth it. And so photovoltaic production of hydrogen would be the best. And there you wouldn't have to worry about it. So that would probably be green. And the gold standard green hydrogen is generated by turning water into hydrogen and oxygen with electricity generated from renewable resources. So renewable resources would be photovoltaics. So we'll get green. Turquoise is not as good as green, but turquoise is somewhere between blue and green. Blue makes it with CO2 as a product. All right, so hydrogen might be another option here in the future. So I don't know, there's no push for hydrogen vehicles right now at all. But there's no infrastructure too. Are there very many hydrogen fueling stations? No. I mean, we're lucky because on 190th, there's a hydrogen fueling station, but they aren't all over the country. If they can dump a whole bunch of money to make hydrogen fueling stations, maybe that's the way to go. But I think electric vehicles have won the race. I think the hydrogens are starting to fade.
Can't you put water in your tank and then use the battery to do electrolysis, pump the hydrogen into the combustion chamber?
Yeah, you could do that too. Generate on demand.
Yeah.
That would work. Well, that's if you had a whole solar array on top of your car and then, generate it. But storing it would be difficult. It's too slow to generate. So, anyway, let's go back to the book here. This is fusion technology. Have you ever heard of cold fusion?
Yeah.
Cold fusion, this was a really interesting idea. In concept, it seems like it would work. Hydrogen is like methane. Both of them are gases. When you use methane, when you store it as a compressed gas, but even a compressed gas has a lot of empty space. And so probably the best way to store methane is to liquefy it. Because if you can liquefy it, you can get a lot more methane per volume. The same thing with hydrogen. These hydrogen cars, is that liquid hydrogen or gaseous hydrogen in there?
Is it stored as liquid?
You'd think they store it as liquid, otherwise the range is going to be terribly short. Your tank is mostly empty space, a little bit of fuel in there. One of the things that people were looking at is storing it, the hydrogen dissolved in a metal like palladium or platinum. It turns out, like in palladium, you can put more hydrogen in a milliliter of palladium than you can have in liquid hydrogen. And so if you had liquid hydrogen, you can only put this many grams. If you had hydrogen dissolved in palladium, you could put more grams per milliliter. in there. And so it's much more dense than liquid. So that got people thinking, well, how is it more dense? How can you squeeze in liquid hydrogen, the atom's already touching. So that means the hydrogen that's dissolved in palladium must be squeezed even tighter together.
That's a topology.
Yeah, if they're squeezed even tighter together, is it possible that the nuclei can get close enough to fuse?
Oh.
And so that's the whole idea behind cold fusion, is by squeezing the hydrogen, somehow palladium's putting the squeeze on the hydrogen, and if it's squeezing enough, then that's already halfway there to fusion. And so that's what they're looking at. It's cold fusion. So that was pretty interesting. All right, so anyway, those are the kinds of calculations we're doing in chapter 7. We're moving on to chapter 8 now. And so chapter 8 deals with chemical reactions. And so we're going to look at evidence, observations of chemical change. We're looking at balancing chemical equations, interpreting chemical equations, writing chemical equations, that kind of stuff. So we're looking at chemical reactions here. In the fuel tank of the space shuttle, they're not going to have hydrogen as a gas. Because if hydrogen is a gas in the space shuttle tank, there's a lot of empty space. And so it's not a very efficient way of transporting or containing hydrogen. So they liquefy it. So we have liquid hydrogen here. They can't put palladium in here. Palladium would be way too heavy. Yeah. Even though you might be able to store more hydrogen in palladium than you can in liquid. It just doesn't make sense. And not only that, palladium is way too expensive. For cold fusion, it might be cool, but for anything else, it's impractical. And the oxygen is also going to be a liquid because that's going to be the most densest path way of doing that. And so here we have liquid hydrogen, liquid oxygen, and we call these the reactants. So anything on the left side of the arrow is reactants. And the arrow just means produces or yields. And so liquid hydrogen or liquid oxygen produces or yields water. This is gaseous water or steam. So the two waters. And lots of energy. So you can see that there's lots of energy. That's why we get into plasma. And so this is actually a bit more complicated than what it looks like, because this is not steam coming out here. You got these big flames shooting out here.
The specific info is only about 300 seconds or so.
Is that it? Wow. Well, that's an impressive sight. So things that clue in, that a chemical change is occurring or a chemical reaction is a change of color. Change of color can be tricky because sometimes it doesn't necessarily mean that there's a reaction. Formation of a solid product. Formation of a solid product is called precipitation. We'll look at an example of that. Formation of gas. Formation of a gas is called effervescence. We'll look at that as well. Heat or light. And so for sure we see lots of heat, lots of light. There's definitely a chemical reaction between the hydrogen and oxygen there. Here's another kind of color change. Here we start off with the reaction here, which produces this purple color, or violet color, which fades. So that's indication that something chemically is changing there. This is precipitation here, formation of solid. So we take two liquids, mix the two liquids together, and we get this cloudy. This is called a cloudy white precipitate. A cloudy white precipitate consists of tiny, tiny white crystals, and these really, really small crystals will eventually settle down to the bottom of the test tube. But for now, they're suspended in the liquid here. And they'll float down. Okay. So this is a precipitation. This is effervescence or gas formation. So mixing this liquid with this solid, and you get these gas bubbles, CO2. Here's light and heat in the flame. So these are all evidence of chemical changes. not physical changes. This is also a chemical change. The glow sticks emitting light. A lot of these cold packs are physical changes. You know, you're taking a salt and dissolving it in water, and it gets cold. In the physical change, we can evaporate the water and get the salt again, and then we can reuse it. So this is a physical change, but sometimes that heat could be due to a chemical change. So it's hard to tell sometimes. In this case, you couldn't tell unless you were told. So what they do is they take ammonium nitrate, solid ammonium nitrate. Not that much, I wouldn't worry about this being too terribly explosive. And they take that solid ammonium nitrate and break the tube it's in, and then it reacts with the water, interacts, just dissolves in the water. We call this endothermic. Endothermic means heat absorbed versus exothermic, heat is released, and so it gets cold. We'll talk about this later when we get to solutions. So, is this a chemical or a physical change? A firecracker explodes. Chemical or physical? Chemical. Firecracker is no longer there. Water evaporates. Is that chemical or physical?
Physical.
That's physical. Water's still there. It's just humid air now. Humidity. In fact, I saw an interesting article over the weekend about humidity. It was, do you know about the seasonal variation of the flu and other respiratory viruses? And that's a pretty consistent observation, isn't that? The seasonal variation. Would you call it the law? The law of the seasons, maybe?
That's a rule.
Well, maybe a rule. Maybe a law. Depends, how consistent it is. You can easily predict it's going to be more severe during certain seasons. Maybe. But it's kind of borderline. But what's the hypothesis there? What's the underlying reason? And so this is kind of interesting because I never thought about the hypothesis of this. I just thought, okay, this flu is seasonal, right? Cold weather. I thought cold weather, you get cold, you're more susceptible to catching the flu. But he had a very interesting hypothesis. This is the guy's Richard Zare at Stanford University. You know what his hypothesis was?
The humidity.
Yeah, the humidity. The humidity has to be between 40 and 60%. If the humidity is between 40 and 60%, then flu transmission goes way down. If the humidity is below 40% or above 60%, it goes up. And so why is that? It turned out because of the humidity. In winter, the humidity is much lower. And his hypothesis is this. The humidity in the air, you have tiny droplets of water. And in these tiny droplets of water, there's some mechanism that's generating hydrogen peroxide in the droplets. And so his mechanism, he proposes that there's some kind of surface interaction that's going on with these tiny droplets that causes water molecules to form hydrogen peroxide. And it's because of the hydrogen peroxide, that's the reason why at certain humidities, the transmission is way lower because the water droplets are killing the hydrogen peroxide, is what he's saying. And if the humidity is too low, the water droplets evaporate too fast. If the humidity is too high, then what happens is the droplets get too big and the hydrogen peroxide concentration goes way down, so it's too dilute. And so it's not very effective. And so you have to be at the right level of humidity. But then there are other people who said, well, this is wrong, because, why should hydrogen peroxide form? And so he's saying, another guy who's criticizing his work said that, it must be due to like ozone in the air. And ozone in the air is reacting with the water, making hydrogen peroxide. And it turns out they did some experiments, and ozone was indeed reacting with the water droplets. And this ozone is a natural pollution. You get ozone when you have the lights on and other stuff. Sometimes you can smell the ozone from electronics. Have you ever
Oh,
That
Yeah.
smell.
That smell from the electronics smell, burnt electronics kind of smell. It's ozone. And so he's saying that ozone reacts with it. So there's an ongoing debate right now about this. And so what they did was they did an ozone-free atmosphere. They did an ozone-free atmosphere, and they did actually generate a little bit of hydrogen peroxide. Not as much, but a little bit. And they said that little bit is enough to kill the viruses. And so that was kind of interesting. So you might want to, get the humidifier in the winter. But well, check the humidity in this room. Maybe I'll put a little bowl of water there. Keep the humidity up in this room to generate more hydrogen peroxide in the water droplets to kill any kind of respiratory virus.
but what's the mechanism that makes the peroxide?
They're still trying to figure it out. They haven't figured it out. This guy is a pretty famous chemist, Richard Zare. I've seen him speak a couple of times about other things, not this hydrogen peroxide stuff. You see, this is of course, whenever you propose something like this, there are going to be people who are going to say, "No way." So this is one of the studies. This is one of the main critics of this is Mishra, who's a professor. Said that this is wrong. There's a study cast doubt on water microdroplets' ability to spontaneously produce hydrogen peroxide. And so after this paper, he wrote a paper criticizing it. And then Zare went back into the laboratory and made sure there was no ozone because this guy was saying it's ozone, it's contaminated. It's nothing new. And so Zare went back into the laboratory and then he made he measured hydrogen peroxide in water in an ozone-free atmosphere. And determined there was hydrogen peroxide, just not as much. Originally it was 30 micromolar, with ozone, but without it was way, way lower than that, but still there was some ozone. Hydrogen peroxide with no ozone. And so this has been ongoing. I've been following this loosely, but Zare made a new article saying that his results still stand, although contamination is definitely a possibility. And then he came up with this hypothesis. This hypothesis was from last year, which was in there it is. This isn't his paper. He wrote a paper on this and published it. He's talking about the seasonality of viruses and the creation of hydrogen peroxide. Other people are saying, one way to minimize it is to get a humidifier and then put hydrogen peroxide in the humidifier and then have a little bit of hydrogen peroxide.
What's the ratio? You could calculate it, right?
Yeah, we can calculate it. But it occurs naturally, according to Zare. It occurs naturally.
Well, how?
In winter, the humidity is way down. But how? That's it. Everybody wants to know how. And so this is why the main critic of his work says, according to the laws, of nature, he can't see how it's possible. It's just not possible.
What about the high static charge in the clouds? Could that have
Oh yeah,
something to do?
that does too. Electric fields.
Yeah, the electric field, could it sort of ionize something?
Right. Electric fields do ionize. Electric fields will. But I think he did shield it. So there were no electric field interferences and no ozone. Electric fields can cause ozone. I used to make ozone too. Tesla coil?
Yeah.
I used to use Tesla coil to make ozone. You can make ozone using UV lamps. Ultraviolet light will make ozone. There's lots of ways to make ozone. So he did it in a light-free, electric field-free, it's totally shielded environment. And
It's a conundrum.
yeah. So anyway, this is ongoing research. So I wanted to point this out just because it's observation, seasonality of flu, and it's a reproducible pattern, which you might call a law, and then this is the hypothesis. And so we're waiting for the theory to come out. The theory would be describing the mechanism of everything else. And this is how science works, pretty much. Yeah, it's really cool. Is it time for break? Yeah, let's take a break now. So is this a physical or chemical change here? Yeah, chemicals. This is actually sodium metal and water. There's a dye put in the water, which changes the color depending on the pH, how acidic or basic the water is. This is the reaction here. Taking solid sodium metal plus liquid water, it produces hydrogen and sodium hydroxide in heat. Oftentimes we don't, there's a lot of heat generated in this, but oftentimes we don't factor in the heat here. We just balance out the atoms. And so the heat, because there's no number on it. If there were a number, then we can put that in here as well. It would be pretty useful. But this is just telling us heat is generated as a product. These are products on the right, these are reactants on the left. But it's not balanced here. We have one sodium, two hydrogens. 2 plus 1 is 3 hydrogens. So the hydrogens don't balance. One oxygen, one oxygen. And so what we have to do is we have to make sure that we balance it. That is, we don't have atoms being created or destroyed. Okay, these are the states. We talked about the states before. And so we balance it by changing the coefficient. So here, to balance out the hydrogens, let's see, the oxygens, the hydrogens. So if we did this, I wouldn't have balanced it in this method. But this is the way they balance it. Let's take a look at some others here. Sometimes this involves trial and error, but there is a system to doing this. So we'll try to balance this one. Aluminum plus oxygen is going to make aluminum oxide. And so this is the system that I do. Aluminum is a metal solid plus oxygen. This is the element oxygen. Oxygen doesn't like to be alone. It likes to form diatomic molecules like this. And then this is going to form aluminum oxide. What's the formula for aluminum oxide? Well, aluminum oxide is an ionic compound. It's a compound of metal and non-metal. Aluminum, what's the charge on aluminum? Yeah, we'll say 3 plus. And oxide, what's the charge on oxide? 2 minus. And so how many of each will we need to add up to 0? Yeah, 2 aluminums, 3 oxygens. One quick trick that people do, if they know the charges like this, is they'll just do this kind of cross multiplication type deal. And so 2 aluminums, 3 oxygens, and then it should balance. So let's do that. The other way is you can just write them out until they balance. And so we should form Al2O3. This is aluminum oxide. Al2O3. And that's a solid. Most ionic compounds are solids. In fact, all the ionic compounds that you're going to see are solids. Okay, this is not balanced. So usually I leave oxygen to last, single element. I could leave aluminum to last too, but oxygen's. And so when I look at this, I have 2 aluminums on the right, but only 1 aluminum on the left. And so the easiest way to balance this is to change the coefficient here. And so I'll put 2 aluminums here. So now I have 2 aluminums. So now the aluminums are balanced. I don't want to touch the aluminum. I don't want to touch the aluminum oxide. I'm going to leave this oxygen for last here. So I have 3 oxygens over here. And so there are 3 oxygens on this side. How many oxygens do I have on this side? 2 oxygens. And so what I'm going to do is I'm going to say x times this. X times 2 is equal to 3. What is x? X is equal to 3/2. This is for oxygen. Here. Well, if x is equal to 3/2, then that's balanced. But can you have 3/2 of an oxygen molecule? No.
No.
And so what we'll do is we'll double everything. So 3/2 times 2 gives me 3. So I have 3 and 3. Now, if we double everything, then that means I'm going to have 4 aluminums plus 3 oxygens. This is going to yield or produce 2 aluminum oxides. 2 or 3 solids. And so now this is balanced. We have 4 aluminums on the left, 4 aluminums on the right, 6 oxygens on the left, 6 oxygens on the right. I'm just going to balance this out. Is this balanced? C2H4O plus 3 O2s yields 2 CO2s plus 2 H2Os. Is it balanced or not balanced? So what we'll do is we'll start with carbons. How many carbons do I have here? 2 carbons. How many carbons do I have here? In 2 CO2s, I'll have 2 carbons also. So the carbons are balanced. No problem with that. Are the hydrogens balanced? So how many hydrogens do I have here?
4
How many hydrogens do I have here?
2
2 times
times 2 4
is 4. So the hydrogens are balanced. Are the oxygens balanced?
1, 2 4. Yeah.
The oxygens are balanced?
Wait. Yeah, 1.
No.
So yeah, I count this as 1 plus 3 times 2 is 6. So 1 plus 6 is 7 oxygens on the left. How many oxygens on the right? So 2 times 2 is 4 plus 2 is 6. So I have 7 oxygens on the right, 6 oxygens on the left. Therefore, is this balanced?
Yeah.
No, it's not balanced. So let's go ahead and balance this one. So if I try to balance it, I'm going to have C2H4O. What the heck is the name of that? C2H4O. Would you name this dihydrogen dicarbon tetrahydrogen monoxide? Would you name it that? No. You would never name it like that because naming it like that is only reserved for binary molecular compounds. This is not a binary molecular compound. We call this a ternary molecular compound. What's the difference between a binary molecular compound and a ternary molecular compound?
2 elements and 3 elements.
Yeah, 2 elements and 3 elements. We only learned how to name binary. So if it were this, C2H4, I'd call it dicarbon tetrahydride. It's fine. But since we have this 3rd element, forget it. And so how do I name that? You don't. You're not going to name this. If you have a ternary molecular compound, don't worry about the name. You know, you have to take organic chemistry, and then you can learn how to name all these. You know, but we're not organic, and so this is outside. You're never going to be asked to name this. Plus O2, but what I'm going to do is I'm just going to leave the coefficients out. This is going to produce. Okay, we should be able to name this one CO2. Everybody knows that. And H2O. Everybody knows that as well. Okay, so what I usually do is I leave oxygen for last because it's just single. If I change this one, it's only going to upset the oxygens. If I change this one, it upsets both the carbon, the hydrogen, and the oxygen, or all 3, carbon, hydrogen, and oxygen. And so let's balance out the carbons first. So how many carbons? 2, and that means I'm going to need how many CO2s? I'm going to need 2 CO2s, so 2 carbon dioxide. Now the carbons are balanced. Then I'll go on with hydrogen. How many hydrogens?
4.
How many hydrogens here? 2. So what should I do?
2.
2 waters. If I have 2 waters, that's going to give me a total of 4 hydrogens. Okay, now I'm going to get to oxygen. So oxygen, do I want to change the coefficient here? There's a 1. If I change the coefficient here, it screws everything up. So that's fixed at 1. Can I change the coefficient here? I can change the coefficient here with no penalty. So this is going to be 2x. So 1 plus 2 times x. X is going to be however many I want of these O2s. 1 O2, 2 O2s, 3 O2s, etc. This is going to be how many oxygens here? 4 plus how many here? 2. Those are fixed. So the only one I want to change is this x here. And so this is going to be 2x. This is going to be 6 minus 1. So 2x is equal to 5. X is equal to 5 halves. And so x is equal to 5 halves here. So if I have 5 halves times 2, that gives me 5. 5 plus 1 is 6. 4 plus 2 is 6. So 6 and 6. It's balanced now. Except we typically don't have fractions here. And so if I want to get rid of that fraction, I'm going to multiply it by 2. This is not a law. So I don't have to get rid of the fraction. But frequently it's done. Because there's no such thing as 5 halves of molecule of O2. If these were moles, yeah, then fractions are no problem. I could have, you could have a half a dozen, right? Well, you could have half a mole, it's not a problem. But you wouldn't go and buy a half an egg. It just wouldn't work. So this is called balancing chemical reactions. We'll get some more practice balancing. Let's see if we can balance this one in our head. Okay, this is methane plus oxygen yields CO2 and water, the combustion of methane. How many carbons? 1, and over here, 1. So we'll leave those alone. Leave oxygen for last. How many hydrogen? Over here, 2. So I need to double this. That's going to give me 2 plus 2. It gives me 4 oxygens. And therefore, this has got to be 2. That's what we get. We get 1 methane, 2 oxygens, yields 1 CO2 and 2 waters. If we're dealing with individual molecules, we can't have fractions. So if we look at an individual molecule, 1 molecule of methane, 2 molecules of oxygen, yields 1 molecule of CO2 and 2 molecules of water. So it doesn't make sense to have fractions. However, if we're dealing with dozens, like if I had a dozen molecules of methane and 2 dozen molecules of O2, then we can have half a dozen. That's not a problem. Or if I had a mole, 1 mole of methane molecules, which would be an Avogadro's numbers worth. So we're supposed to draw pictures here. The pictures would just look like this. Let's try to balance this one here. This one looks a little bit more involved. If I have oxygen, which is a single element, O2, then that's one I want to save for last, but this one doesn't have that. And so we're looking at PCl5 solid plus H2O liquid yields H3PO4 plus HCl. Okay, H3PO4 is AQ, and HCl is AQ. Okay, so can we name these? What's the name of this first one here? PCl5. Should I call this phosphorus chloride? Or phosphorus pentachloride? Yeah, this is a binary molecular compound. Molecular compounds are nonmetals. Phosphorus is nonmetal, chlorine is a nonmetal. It's a binary molecular compound. We're going to call it phosphorus pentachloride or monophosphorus pentachloride. But we get rid of that mono and just call it phosphorus pentachloride. This is also a binary molecular compound. So should we call this dihydrogen monoxide? No, because the common name, everybody should know the common name for this is water. So phosphorus pentachloride plus water yields what? What is this? H3PO4. Well, first thing you should recognize is this has got to be trihydrogen monophosphorus tetroxide, right? Or wrong? No, we can't use that naming system for this. Why? Yes, more than two. But if we only had two, yeah. So if we're this, then no problem. But we have three, so we can't use it. And so how do we name this? Well, either we don't or we do. In this case, we do because if the compound begins with an H, we either call it an acid anion or an acid. This is going to be an acid because there's no charge. So if this is an acid, we only have three choices. You know what the three choices are? The three choices are, it's going to be a hydro, ick, or it's going to be an ick, or it's going to be an else. Those are our three choices. Which one is this?
Else.
Well, it depends on the anion. And so what is the anion? So can you tell me what the anion is? It's PO4 with what charge? It's got to be a PO4 with what charge? Minus?
One minus.
One minus? And then what is H? What's the charge on H?
Plus, one plus.
Yeah, and how many plus ones do we need to cancel out a minus one? We only need one hydrogen to cancel that out. But we have three hydrogens. And each hydrogen's plus one, which means PO4 cannot be minus one. If we have three hydrogens, to balance out the charge on PO4, the charge on PO4 has got to be,
Minus 3.
yep. You might want to try these drills here for nomenclature. Do you know what borate is? Borate. Borate is BO3 3 minus. Borate's BO3 3 minus. So borate, BO3 3 minus. Carbonate. CO3 2 minus. Nitrate. NO3 minus. Fluorate. FO3 minus. Chlorate.
CO2.
ClO3 minus. Bromate. BrO3 minus. Iodate. IO3 minus. So on this elbow here, all the 8s have three oxygens, right? Three oxygens, BO3, CO3, NO3, FO3, ClO3, BrO3, IO3. What happens to the charge? The charge counts down 3, 2, 1, and then stops at 1. You see that? So this is borate. And the next, we're going to go to silicate. What's silicate? Yeah, silicate is well, it's an anide. These are going to be the anides over here. So it's not +4, it's the opposite, -4. And how many oxygens are on silicate? So this outer elbow here has 3. The inner group has 2, not 2, 4. So silicate is SiO4. Remember, it's group 4 or 14, group 4. SiO4 charge, 4 minus. So silicate's SiO4, 4 minus. Phosphate is PO4, 3 minus. So this is PO4, 3 minus, which means this is phosphate. And so if we have an IDE, monatomic I or polyatomic I, then it goes to hydro-ic. If we have an 8, it goes to ic. If we have an I, it goes to else. And so we have an 8, and so we expect ic. And so this should be phosphoric acid, but phosphoric acid sounds funny, so we call this phosphoric acid. Phosphoric acid. So silicate's SiO4, 4 minus, phosphate's PO4, 3 minus, sulfate is SO4, 2 minus. Selenate
Should be phosphoric acid.
Selenate is SeO4 tellurate, STEO4 2 minus. Arsenate is ASO4 3 minus, like phosphate. Germanate is GeO4 4 minus, like silicate. And so there are 2 patterns here that you should just memorize.
Is there a name for those like sections, or is it just like a?
Yeah. There's some theory that underlies this. I mean, once you understand the theory, then it's clear why we see the pattern. And so, we don't really. These ones you will see later why. These ones are going to behave differently than these inner ones. We'll see that later on. I mean, we need a little bit more theory to understand it. Right now, we're just looking at the observations. And so the way I do this is I just go borate, BO3, 3 minus carbonate, CO3, 2 minus nitrate, NO3, 1 minus chlorate, chlorate, bromate. Just do that. And then just repeat these. And just chant or mantra or whatever. And so this would be phosphoric acid because it ends in 8. This one does not end in 8.
Hydrochloric acid?
Yeah, this would be hydrochloric acid because chloride ends in I. And so if it ends in I, then it's hydroic. So this is hydrochloric acid. And so when PCl5 reacts with water, it forms phosphoric and hydrochloric acid. What we want to do is we want to balance this. So how many phosphoruses? 1 over here. 1. So it's balanced. How many chlorines? 5 over here. Only 1. And so I need to change the coefficient to 5. Okay, that balances PCl5 there. How many hydrogens? 2. Over here I have how many hydrogens? 3 plus 5 is 8. 8 hydrogens. This is not balanced. So I'm going to change this one to 4. And then hope the oxygens work out. And so let's check the oxygens. 4 oxygens here, 4 oxygens there. So now it's balanced. And so we had phosphorus pentachloride plus water yields phosphoric acid and hydrochloric acid. So now it's balanced. Okay, what's the name of the first compound there? Are you expected to know the name of that first compound?
No.
No. Although people will try to name it like dicarbon, pentahydrogen.
I think we talked about this one like last time.
Oh, did we?
Because I just remember the CH8, COO8.
It's because it's propanoic acid, isn't it?
This one? Yeah. This is called propanoic acid.
Yeah.
That's
I
right.
think it's last time we were talking about acetic acid.
Acetic acid? Yeah, it could be acetic acid last time. This acetic acid is also called ethanoic acid. This one, the acetic acid is 2 carbons. This one has how many carbons there? 3. It's a little bit tricky because they don't write them together. It's separated. And the hydrogens are separated too. So we have 3 carbons. How many hydrogens?
6.
6 and 2 oxygens. Then this is plus O2, so we're just going to burn this stuff. And we're going to form CO2 and water. So we leave oxygen for last because that's going to not impact other elements. And so we have 3 carbons here, 1 carbon here, so I'm going to multiply this one by 3. And then how many hydrogens do I have? 6 hydrogens, so I'll multiply this one by 3. That's going to fix the oxygens here. So 3 times 2 is 6, plus 3 gives us 9 oxygens here. And when I look over here, how many oxygens here? 2, and I can't change that, because if I change that, this is going to screw up carbon and hydrogen. What I'm going to change is x here, and so I'm going to call that 2x. So 2 plus 2x is equal to 9. So that means 2x is going to equal 7. X is going to equal 7 halves. And so this x here equals 7 halves. So does that balance? Let's see. I'm going to have 2 plus 7 is 9. 9 oxygens, 9 oxygens, so it balances. So 7 halves is correct. And then what we can do is we can double everything. So if we double everything, then I'll have 2 of these, which is propanoic acid, plus 7 O2s. We're going to produce 6 CO2s, plus 6 H2Os. H2O is a liquid, CO2 is a gas, O2 is a gas, and propanoic acid is a liquid. You don't need to know the name for propanoic acid. When we have a balanced chemical equation, there are different ways we can visualize what's happening there. One is we could look at individual molecules. So 2 molecules of hydrogen reacting with 1 molecule of O2 gives us 2 molecules of water. Or we could look at it in dozens, like 2 dozen hydrogen reacting with 1 dozen O2 to give us 2 dozen H2O molecules. Or we could look at it in terms of moles. If we look at it in terms of moles, then it's going to be huge. There's the Hindenburg there. Okay, so what we're going to look at next are writing these out and then looking at different types of chemical reactions that occur. Here they're trying to get us to classify it, but we'll try to do a little bit more than that. So what's the first reaction? This is magnesium or magnesium ion?
Magnesium.
Okay, so we have magnesium. Magnesium is normally what? Solid, liquid, or gas?
So,
Magnesium metal. Plus N2 is called nitrogen or nitride. This is nitrogen gas, elemental. So the elements on the right side of the periodic table, this is two elements. The elements on the right side want to take electrons or give up electrons. On the right side of the periodic table, they want to take electrons. Left side, they lose. And so magnesium is going to lose. How many electrons will it lose? What's the typical charge on magnesium, or the only charge on magnesium? It's going to be 2 plus. And then nitrogen wants to gain how many? 3. And so this is going to be N3 minus. And then we'll do the little trick here to figure out how many of each we need by just doing this kind of cross multiplication type deal. 2 for the nitrogens, 3 for the magnesium. So what we're going to form is Mg3 N2. Do you know what we call this? This is called, well, is this what type? Is this a trimagnesium dinitride? Trimagnesium dinitride. Yes? No. The reason it's no is because this is not a molecular compound. When we have a metal and a non-metal, we call it an ionic compound. And it consists of the ions magnesium and nitride. Where it gets confusing is with the acids. But this should just be named as the cation, magnesium, and the anion name, which is nitride. So this is called magnesium nitride. If this is magnesium nitride, then I know what the charges are. Magnesium's 2 plus, nitride's 3 minus, and then I know what the ratio is. So I don't have to tell anybody what the ratio is. They should be able to figure out what the ratio is based on the charges. And so magnesium metal reacts with nitrogen to form magnesium nitride. Is this balanced? No, we need to balance it. And so how can I balance it?
we're gonna use magnesium more.
Yeah. And then it looks like it's balanced. Now this nitrogen is different than this nitrogen. This nitrogen is 2 nitride ions. This nitrogen here is what we call a molecule of nitrogen. And so they're different. So it just happened that this was 2. It could be 3 or 4 or 1. We could have different amounts of nitride depending on how many we need to neutralize the charge, how much positive charge we have. This is called a combination reaction. And this is an element plus element combination reaction. Taking one element and another element. So element plus element combination reaction. Now this is what we call redox. Nitrogen's not that great of an oxidizer. You know, the species that's taking electrons, the oxidizer. Nitrogen's not that great, not nearly as good as oxygen. But, you know, sometimes it can oxidize metals. The metal here is called the fuel or the reducer. So let's take a look at the next reaction here, which is this, ZnOH2. What's ZnOH2 called? ZnOH2, zinc hydroxide. This is zinc hydroxide. Zinc, you should recognize zinc. What's special about zinc? You know, when we look at the charges on the periodic table, we can get most of the charges off the periodic table. These are all +1, these are all +2, these are all +3. Over here, these are +3. But everything else is variable charge except for 3 of them. Everything else is variable charge except for copper is variable actually, because we have copper +1 and copper +2. And so not copper, but we have zinc, cadmium, and silver. I saw an interesting article about zinc. You know, people need a little bit of zinc, you know, for good health, right? Immune health. If you read the bottle of zinc supplement, it says good for immune health. But do you know what ants use zinc for? Ants. This is a pretty interesting article. Like ant teeth. You know, ant teeth are really small, but somebody studied these like atom by atom. And it turns out that ant teeth use zinc. And so they did some atomic scale imaging reveals ants use zinc to sharpen their teeth. It's pretty interesting because this is University of Oregon, team of biophysicists. But it's pretty interesting because these are extremely sharp. And they, you know, if an ant bites into something, it requires 60% less force than if humans were to bite into it. And so it's pretty interesting. I don't know if it's zinc ions or zinc atoms. You know, the zinc ions, they say that zinc is right on the edge, you know, the cutting edge of the teeth. Human engineers might also learn from this biological trick. So I wonder if we put zinc, you know, zinc fillings or something like that. Or have some sharp zinc edges on the teeth and make things. But anyway, what you have to remember is that we're going to have 3 fixed charge species. These fixed charge species, zinc's always +2, cadmium's always +2, and silver's always +1. So we don't need Roman numerals here. So this is just called zinc hydroxide. All the other ones will have a Roman numeral in that kind of general region, like copper. Okay, zinc hydroxide plus, what's the other species? H2SO4 plus H2SO4. What's H2SO4 called? Well, first off, is this an acid or an acid anion? Or neither? Well, an acid anion would have a charge. This has no charge. This is an acid. Acids begin with H. So this is an acid. If this is an acid, then we need to know the anion. The anion is going to be SO4. But what's the charge on SO4? We can figure out by how many hydrogens we have, because each hydrogen is +1. So if we have 2 hydrogens at +1, what must the negative charge be on sulfate to add up to 0? Yeah, it's going to be 2-, and we call this anion what? Sulfate. That's good.
Sulfuric acid.
Right. Sulfuric acid. So we can go back to the periodic table. You know, this is 4 oxygens, and the charge goes 4, 3, 2. So it's sulfate. So this would be sulfuric acid. Right. Sulfuric acid. So if we take zinc hydroxide and mix it with sulfuric acid, what do we expect to happen? And so these are 2 ionic compounds, and when we mix 2 ionic compounds together, one of the things that might happen is we might just exchange partners. So for example, right now, hydroxide's partnered with zinc, and sulfate's partnered with H. And so what we do is we see, if we switch the anions, will we get something that could be more stable? And so what we're going to do here is we're going to take zinc and pair it with sulfate. Well, zinc is 2 plus always. Hydroxide is 1 minus. So if we take zinc and pair it with sulfate, well, it's going to be a 1-to-1 because 2 plus 2 minus, we'll end up with ZnSO4. What do we call ZnSO4? Zinc sulfate. So we'll end up with zinc sulfate. And we're going to pair up hydroxide with hydrogen. And so if I have H plus, how many H pluses, how many OH minuses do I need to balance it out? 1-to-1. And I'm going to form HOH. HOH is also known as water. And so this is going to form H2O. Okay, now when we balance it, we typically balance by ion. When we have ionic compounds, it's easier to balance by ion rather than atom. So how many zinc ions do I have here? I have 1. How many zinc ions do I have here? 1. How many hydroxide ions do I have here? How many hydroxides were there to balance out the zinc? Actually, I'm going to need 2 hydroxides. There are 2 hydroxides here. Over here, how many hydroxides? Well, each water only had 1 hydroxide. It was 1 hydroxide plus 1 hydrogen ion. So I need to double this and double that and then double this. So I'm going to have 2 waters. And then over here, I have 2 hydrogen ions. Up here, I have 2 hydrogen ions after I doubled it. Here I have 1 sulfate. Here I have 1 sulfate. So now it's balanced. And so this is zinc hydroxide plus sulfuric acid yields zinc sulfate plus water. And that would be the balanced chemical equation for that. Okay, figure out what's going to happen in number 3. What am I mixing together in number 3?
Zinc and iodide.
Okay, I'm mixing zinc ion or zinc metal? Zinc metal, which is solid. And iodide or iodine?
Or it's iod because that's a diatonic, right? It's
Yeah.
Iodide.
Iodine, yeah. And so this will be I2. I2 is actually a solid. Br2 is a liquid. Cl2 is a gas. All right, so figure out what's going to happen here. This is what we call an element plus element combination. Let me know when somebody figures it out.
Would it just be ZnI2? Because they're balanced. They're already balanced with electrons.
Yeah, so zinc is going to gain or lose electrons in this. It's going to gain or lose? Lose. And so we're going to end up losing how many? Two. And then iodine's going to gain or lose? Two or one? For each iodine. Yeah. Each one's going to be. And so we'll need two of those. So it comes out to ZnI2. This I2 is not the same as this. This is two iodine atoms that are bonded together that are neutral. This is two iodides. Just by coincidence, it came out 2 and 2. Sometimes we need 3 iodides, like for example, aluminum, we need 3. Zinc iodide, what would you suspect, solid, liquid, or gas? Solid. Ionic compounds are solids. And so that would be it. And so this would be called a redox reaction, and this is an element plus element combination redox reaction. Redox reaction means somebody lost electrons, somebody gained electrons. So, but this is called the oxidizer here. The oxidizer took the electrons. Is iodine a very powerful oxidizer? Yes? Yeah, it's a pretty decent oxidizer. Is it as good as chlorine? No, it's not as good as chlorine. Which is a good thing, because I gargle with iodine. So mix it with water and gargle with it.
Actually got that one.
Fortunately, it's good enough to oxidize viruses and bacteria, no problem. To oxidize that, but it's not powerful enough to kill you. So that's good. PbO2. PbO2 goes to what? Now, PbO2, what is the name of that? PbO2. Is this a binary molecular compound or an ionic compound?
It's an ionic.
It's an ionic. So we wouldn't use the binary molecular. Binary molecular would be all nonmetals. We call this lead dioxide. Although some people do call this lead dioxide, it's not the proper name. The proper name would be lead 4 dioxide.
No, it's like that P with plumbus.
We can use plumbus and plumbic, but that's optional. Yeah, you don't have to memorize those. This is going to be lead 4 is correct. Lead 4 because it's Pb4 plus, and then we have how many oxides? We have 2 oxides. So do we need to call this lead 4 dioxide, or can we just call this lead 4 oxide? Like over here, did I call this zinc diiodide or just zinc iodide?
Because it's the diatomic, so you don't have to.
This diatomic and this diatomic are two different things. Here, I call this zinc iodide. I call it zinc iodide because in ionic compounds, we can figure out the ratio. I don't need to call this diiodide because I know I have to have 2 iodides for every zinc because of its charge. Mm-hmm. The same thing here. If I have lead 4, I already know how many oxides I have to have. I don't have to be told it's di. And so this is actually only called lead 4 oxide, not dioxide. Dioxide would be incorrect because we already can figure out it's going to have 2 oxides for every lead 4. Okay. So lead 4 oxide. What happens here is lead 4 oxide is stable. Lead 4 oxide you find in car batteries. This is what they call the cathode of a car battery. But what you can do is you can heat this up. If you heat it up, what can it decompose into?
Lead and oxygen.
Yeah, it could decompose into lead, metal, and oxygen gas. So this is the reverse of oxidation. If I think about oxidation of lead, it's the reverse process here. Lead, metal gets attacked by the oxidizer oxygen. Mm-hmm.
When you heat up metals, they tend to oxidize.
Yes.
But in this case, the heat separates.
Well, it's already oxidized. So in this case, you keep heating it up, and eventually you might be able to reverse this and go backwards.
Oh.
And so this is what they're doing. This is probably going to form molten lead. Most likely it'll form molten lead if you heat it hot enough. And so what this is called is a decomposition. And what's happening here is it's just reversing the process. We're going from lead 4 to lead 0. And for oxide to O0. And so we're just giving the electrons back to lead in this. And so it has to be heated up really hot to do this, to force the electrons back. And so this is called a redox decomposition here. Okay, let's go on to number 5. What do you call Al? Aluminum. Solid, liquid, or gas? Solid. So that's just the aluminum metal. And what's CuSO4 called? But there's a problem. There's 2 copper ions, copper 1 and copper 2. Is that copper 1 or is that copper 2? Okay, so copper 1 will have a plus charge. And then what's the charge on sulfate? 2 minus. Do the charges balance? No, if it's copper 1 sulfate, I need 2 copper 1s. But I only have 1 copper. Therefore, if I only have 1 copper, it must be copper 2. So this has got to be plus 2. And so this is going to be called copper 2 Roman numeral sulfate. Copper 2 sulfate. Copper 2 sulfate, solid, liquid, or gas? Solid. So ionic compounds. Ionic compounds are solid. Now, there are certain patterns that we see that happen. One of these patterns is this. This is called the A plus BX pattern. A is aluminum. B is copper 2. X is sulfate. The A plus BX pattern produces AX plus B. So I'm going to form AX. A is aluminum, X is sulfate. So AX is going to be aluminum sulfate. What is the formula for aluminum sulfate? Well, we'll have to figure out the formula for aluminum sulfate. The first thing is aluminum ion. What's the charge on aluminum ion? Yeah, 3 plus. So we have aluminum, which is a 3 plus, and then what's the charge on sulfate? Sulfate is 2 minus. Okay, to get the ratios, I'm going to use a trick. That is like cross multiplying. So to get the ratios, I'm going to have 2 aluminums. So I'll call it Al2. And how many sulfates? 3 sulfates. And I'm going to need parentheses here for the sulfate. And so I should form aluminum sulfate, which will be my AX. And then B. B is going to be copper. But when copper is alone, it has to be neutral. And so it's going to form copper metal. Copper solid, the element. And so this is an element plus a compound yields a compound plus an element. So element, aluminum, plus a compound, copper 2 sulfate, yields a compound, aluminum sulfate, plus the element, copper. Yeah. This is a redox reaction. This redox reaction is called single replacement. The last reaction that we did up here, the zinc hydroxide and H2SO4 is called a double replacement. DER stands for double replacement. And we replace the anions there. This is a single replacement. I don't know the origin. Oh, I'm not going to worry about it too much. And so it's going to form aluminum sulfate and copper metal. And so this is the pattern that we'll see. Element plus compound yields compound plus element. Let's balance it. Let's leave aluminum for last. And so first we'll balance it with the copper. Let's balance out the sulfate. If we balance out the sulfate, I only have one sulfate here, but I have how many sulfates here? Three sulfates. Yeah, 12 oxygen, but three sulfates. And so I'll need 3. That's going to give me 3 coppers, which I'll put 3 here. And I have 2 aluminums, which I'll put here. 2 aluminum. And so this should be balanced here. So it's a single replacement. If you look at number 6, does that look like a double replacement or a single replacement? Yeah, number 6 is what we call double replacement. And so with a double replacement, it's is FeCl2 called? FeCl2. Yeah, except iron's variable charge or fixed charge. And so which iron is that? Yeah. And so what we call this iron, Roman numeral 2, chloride. Plus Na3PO4, Na3PO4. What's the name of this? Should I call it, this one I don't call iron dichloride. Why? Because it's an ionic compound, metal plus nonmetal. Ionic compounds, we don't use the prefixes, only binary molecular compounds. So this one, I'd like to call it trisodium phosphate. In fact, if you look on boxes of detergent, oftentimes the key ingredient is trisodium phosphate. But that's not the rule, using the rules that we're using in the book. This is an ionic compound, metal plus nonmetal or ions. And so we're just going to name it according to rules for ionic compounds, sodium and phosphate. So we can just call this sodium phosphate. We know we have to have 3 sodiums because phosphate is PO4 charge. Phosphate is PO4. Yeah, PO4 3-. It's like this. You just go back here. Silicate is SiO4 4-. So SiO4, phosphate, PO4. Sulfate is SO4. And the charge goes 4, 3, 2. And so this is going to be 3-. And so we know we have to have 3 sodiums, otherwise it won't balance out. And so it's not necessary to have trisodium monophosphate. The sodium phosphate is fine. Okay, this one is what we call double replacement, and we're going to just switch partners. When we switch partners, it's like this. I'm going to form iron 2 phosphate. And so iron 2 phosphate. Iron 2 phosphate. And sodium chloride. Sodium chloride. So I'm just switching it. Iron 2 with phosphate, sodium with chloride. What's the formula for iron 2 phosphate? So iron 2 is Fe2+, phosphate is PO4 3-. So we'll use our little trick. And so that means Fe3PO4 2. So this is going to be Fe3 parentheses PO4 2. That would be iron 2 phosphate. Sodium chloride. Sodium is +1, chloride is, and so this one's just 1 to 1. NaCl. And then we need to balance this. To balance this, 1 iron, 3 iron, so 3. That gives us 6 chlorides, 1 chloride, we'll put a 6 there. And then I have 3 sodium, 6 sodium, so I'll put 2 here. And then it's balanced. So, all right, we'll stop here and then we'll continue this.